So we have three equations, three unknown variables, x, y, and lambda. And this is a nonlinear system, which means that we are, but anyway, we can. Most of the time, you will be talking about substitute. We are not supposed to divide by x or by y because it could be zeros. We can because lambda is a non-zero parameter, but then that rarely is used. Done here. I use all these twos on the first set of values, and then got this system. So this is the same system as we started with, except no twos on the second. Now, I look at the second equation. Remember that you are not supposed to divide by y because that implies that y is not 0. Could be 0. So what I'm doing, x times y is y. Well, x is lambda because there's equal sign is y and y. I did not. I'm comparing left side to right side, and I see that y's are the same, that x and lambda have to be the same. That's a little bit different concept than divide by y. I am allowing here, so as I said, by comparison, y could be 0. We have to be mindful of that. If you divided both sides by y and got lambda equals, in that case, you are eliminating possibility for y to be 0. So that's a little bit tricky, but that's what it is. So now I have that lambda is x, is lambda. I plug that into this equation, so this becomes x, so that's the x squared. Circle for y squared, get this, get 3x squared, get x squared is 1/3. Now, yeah, I know it's Calc 3, but I still have to say it. You lose your, when you square root both sides, plus minus. So, minus root of 1/3, when you rationalize, you get root 3 over 3, minus root 3 over 3. And then you have the constraint equation x squared plus y squared equals to 1. You know that x squared is 1/3. That means that y squared must be 2/3 because 1/3 plus 2/3 is 3/3, which is 1. So y squared must be 2/3, which means square root again. And we get these 4 points now. We have 4 points because the combinations of plus and minus in front. So we can have root 3 over 3, comma, 2 root 3 over 3. The next point is root 3 over 3, comma, negative 3. And then, what happened? Those are the x and y coordinates at which min or max occur. But then we have to check which one is which by computing z values. Root 3 over 3, negative root 3 over 3, and negative 2 root 3 over 3. So all you need to do now is to compute f of each one of these. So f of root 3 over 3, comma, 2 root 3 over 3. Our function was x times y squared. So root 3 over 3, which is 2. When you square it, you get, well, let's write it. So that's going to be squared, 3 cancels 3, so over 3. 4 root 3 over 3. And observe that since y is squared, value. Because when you square a negative, it becomes a positive, which is again 4 root 3 over 3. Now we go and we compute f of negative root 3 over 3, 2 root 3 over 3, which is negative for both. Max, min. Yes.
Doesn't that square the bottom of the denominator?
Yeah, but it cancels the 3 because this square is 3 and this is a 9. And then 1, 3 cancels. Oh, but 1, 3 stays. So, so these are all 9s. These are all 9s. Denominators in answers are 9. Z value is no input. Because we are just computing f of the input xy, giving us z. So where is the maximum? Maximum is at root 3, 2 root 3 over 3. That's where the max is. So procedure for Lagrange, you have f of x given, f of I given, I given. Obviously the fun is when you have to find them. To you, we'll take a look at that. So that's also there. Then you find partial f, partial y, partial x, and partial y. Del f, which is a vector. So that's a vector of partial derivatives. B, vector of partial derivatives. And then you unleash the equation for Lagrange to solve this. All of this is done in 3 variables as well. There you will have a z, and then one more vector, and it will eventually give you 4x4 system. Your equations come out of here. Depending on number of independent variables, you're going to have that number plus 1 equations. The last equation, the additional equation that you need, is always your constraint equation, which is given to you. So if you remember the problem where you have a cube with a square base, right, you want to make a box with a square base, and what is the minimum amount of material, so, right, blah, blah, blah. Or what is the maximum volume that can be of the square base? Because 2 variables in Calc 1, x and y, right? Calc 3 now, no longer required. You are no base. You can have a base that is, I don't know, one way than the other. And then look for minimum amount of material, for maximum volume, and so on. You have your constraint equation. That's going to be whatever they say to have, I don't know, packaging 8 cubic feet inside the box. All right? So that's a requirement. Next example. Here is the wonderful example. Let me see what you're going to do here. Huh? Oh, you don't see it yet. It's coming up for the projector. I'm not sure why. Yeah, the network is not performing. Yeah. I'm going to erase good luck, and I'm going to write minimum distance to a plane. Find the point on the plane. Two x plus 3y plus 2x plus 3y minus 10 equals 0. Closest to the point. negative 251. So this is one of the simpler problems that you can have as a word problem. What are we doing here? We are going to find the closest what? Closest what? What are you trying to find? Hold on from calculations. Let's talk. Do we understand the problem at all? You are trying to find the coordinates of the point. Okay, fine. What are we either maximizing or minimizing here? Which concept? When you read this problem, which concept you are either maximizing or minimizing? I just toss all the words until something gives. Yes. What happened over here? Distance. You guys see that? You are looking for the closest distance to the plane. You see the wall? The wall is a plane. My head over here is a point. What's the closest distance to the wall? Because you can see it. So yes, because observe, the point is right here. That's the negative 251. 2x plus 3y plus 6z is the wall. What is the closest distance between this point and the... Would it be where the yellow paper is? No, because there's a much shorter one right there. Much shorter distance between this point and the wall. There's a point here, right? There's a point here. There's a point was the closest one because the point was... There's the distance formula from here to... And you know what the cool thing is? This point over here is unknown, which means x, y, z. It could be anywhere. So that's cool. I'll have variables to work with. You stretch the distance point, the distance formula between x, y, z, unknown point, and negative 251, known. That gives you what you're optimizing. That's your optimization equation, because that distance needs to be equal to a minimum. And then here's your G. So in this particular F is something that is not readily available. You have to figure it out that you are looking for the distance between the point, the unknown point on the plane, closest, minimize the distance to the point that is fixed. So we start this by distance formula is going to be x plus 2 squared plus y minus 5 squared plus z minus 1 squared. That is your f of x, y, z. Uh-oh, 3 variables, 3 on the parameter, 4x4 system coming up. And this is the one that needs to be a minimum. So, gxyz is equal to 2x plus 3y plus 6z minus 10. Let's go. Del F vector of partial derivatives. Wow. Chain rule, and the big square root is preserved. So the derivative of this is going to be 2x plus 2 divided by the 2 times square root. Then these cancel. Comma. Next one. 2 times y minus 5 divided by 2 times the square root, these guys cancel. I'm taking partial derivatives of f, which is d. And then another one, 1/2, negative 1/2, so 2 times z minus 1 divided by 2 times the square root, these die. There we go. Del G, cheap. 2, 3, yay. Set them equal to each other using the parameter lambda. So now what we got? We got first equation, x plus 2 over the square root is equal to 2 lambda. Next equation, y minus 5 over the square root is equal to 3 lambda. And z minus 1 over square root is equal to 6 lambda. And we have our constraint equation, g, 2x plus 3y plus 6z minus 10. Well, you can just say equal 10. There we go. You are working hard. You are working hard. See you next week. I thought you were coming for the market. Here. Algebra, exactly. So figure it out. It's lagging because so I have speed on. I have. Yeah, I did right out. It's my full squared. I don't want to drag that around. I'm bored.
I can see it perfectly.
I can still drive it once. I'm still driving. We agreed to what? After this meeting. For real. Seems to like sometimes. Okay, let's try and solve this now. Since you all got it, it's awesome. So, how are we going to solve this? Well, in this case, we have this square root, which is which appears in all three of these equations. So we might want to try and solve for the square root, see how that works. So square root would be equal to x plus 2 over 2 lambda. And then the square root will also be equal to y minus 5 over 3 lambda. And the square root will also be equal to z minus 1 over 6 lambda. And now by equaling these square roots, you can get equations x plus 2 over 2 lambda is equal to y minus 5 over 3 lambda. and let's say x plus 2 over 2 lambda is equal to z minus 1 over 6 lambda. Now, if you pay attention, just die. So we are left with this equation, fairly simple to solve. Now cross multiply, we get 3x plus 6 is equal to 2y minus 10 plus, no, 6x plus 12 is equal to 2z minus 2. We still have the 2x plus 3y as a constraint. So now what do I have? The first equation over here is 3x minus 2y is equal to negative 16. And then I have 6x minus 2z is equal to negative 14. And I have 2x